Okay, so today I'm going to talk about graph databases in Neo4J. There's lots of logic database models has been proposed in the history of database. In this class we talk about relational, but actually that is not the only one. There are lots of past database models that have been proposed. They start with hierarchical that's offered by IBM IMS product, and there's a network model that is proposed by a group called the Codecell, and of course you have already very familiar with relational data model. So the key message here is what goes around comes around. So graph database uses data models that are spirit successors of network data model that is very popular in the 1970s. And the Codecell has a name called Committee on Data System Languages. Here I'm just showing you one network models that will be remarkably familiar compared to the graph models that we will talk about today. So the first graph model that I'm going to introduce is called edge label graph. That we assign labels to edges that indicate the different types of relationships between nodes. By the way, if you have any question, feel free to type in the Zoom chat or interrupt me. So in this, as shown here, picture here, we actually trying to use three nodes. That's one first is Steve Carl, and second is the Office, and the third is BJ Novak. We try to model the Office TV show's crew using this edge labeled graph. So we have three nodes: Steve Carl, the Office, and BJ Novak, and we have three edges. Two has a label called Xin, and the one has a label called produces. So if you actually see here, we have a triple kind of like triple tuple here. We have a Steve Carl is a node, Xin is the edge label, and the Office, which is another node label. So this kind of representation of edges actually form the basis of resources description framework (RDF), or someone will call it a triple store because as you can see, this tuple has exactly three components: the nodes, edge label, and the node label again. Today's focus actually will be on this the property graph models which extend the edge labeled graph with labels. The key here is that we still again using the same kind of data. We have Steve Carl, the TV show The Office, and the person BJ Novak. But what's new in here is that we have a set of key value pairs that serve as attributes that directly attached to each node or the edge. For instance, we have first node. We have a node N1 with a label person, and we have two pairs. The first, actually, we call it property value pairs. The first pair is a name, has a key name, and it has a corresponding value, Stephen Carl. And the second pair, we have a key gender, and we have a corresponding value male. Similarly, for the edge, we have a key value pair as well. In this case, we have a row, which corresponding value is Michael G. Scott, and we have a reference, which is Wikipedia. That's exactly what I should talk about. So let's first compare how's the difference between property graph and edge label graph. So there are clearly two advantages here. Having node labels as part of the model can offer a more direct abstraction that is easier for users to query and understand. So for instance, in this case, it may look obvious that Steve, Carl, and BJ Novak are English names, and of course we are talking about persons. But in a generic kind of like for instance, social network graph, that difference may not be easily tell. So in that case, you can have a very generic label as a person, and then you can have specific key value pairs that indicating different person's name. That will give a very users very good understanding about what exactly each node trying to model. And second point is that property graph actually have actually more advantage in terms of if we want to add in new metadata information. For instance, the metadata information can be modeled as a key value pair of property attributes. If in the edge label graph, if we haven't really think about everything clearly, if we want to decide to add a metadata information later on, then in the edge label graph case, then we may need to refactor the graph, meaning that we need to restructure the graph. However, in the property graph case, if you have even if you have you are missing node or like metadata information, you can easily modify your graph without really going through like lots of refactoring. So here I'm showing the exactly same data, but actually using the relational model. This one probably looks very familiar. Here is actually we have 4 tables here. The first we have 2 base tables. First is a person, and the second is a TV show. We also have 2 tables that we try to model the edges. First is X in, and the second is the producers. Actually, to keep the data consistent, we need to have some key constraints like shown here. We have for instance, X in ID1 has to be a foreign key references the PID that is in the person table, and etc. And also, as you can see, the data here can be a little bit redundant because we need to have multiple part of the primary key show up in different tables in order to keep the data consistent. So that leads to a point that how the property graph can be a good use compared to the relational model. The first point is that graph structure is actually more intuitive than a collection of tables. For instance, you may have experience in the homework 7 that you are trying to model a little bit org chart. That may not be very obvious that at first glance. That is, however, along that way, that if you are using property graph, you can just directly jump into model the data because it's kind of like just like a graph. And it's more accessible for like people even not in have a database expertise like in management, for instance. The second point is actually is that we can avoid repetitive data storage from a user perspective. So like we have seen in the previous slide, we don't really need to store the primary key or foreign key in the property graph. Whereas in the relational model, in order to have a consistent of data modeling, we need to have those data populated almost everywhere in different tables. And also I try to emphasize here is that from user perspective, because underlying that and behind the hood, the property graph actually model the vertices and the edges still as a records. So somehow it just actually the data model hide that a level of details from the user, so that you really don't need to bother about the primary key, foreign key, and repetitive data storage. The third point is that actually property graph allows us to have the same relation name with different attributes. For instance, in the block graphs, for instance, we want to have another, say, a TV show that have another key value attribute that's called production company. We cannot do that in the relational database rather than like drop schema and recreate one, for instance. Because the TV show as a relation name has already been taken by some other table. That's however, in the property graph case, we can easily add another node with label called TV show that actually have one extra property key value pair called production company. So that is the flexibility offered by the property graph data model compared to relational model. And last of all, we have nice query languages that will help with the graph problems. That may be hard. That may be very hard. That you want to say write some graph algorithm in the SQL. Then probably you want to think about any like something like store procedures. Or you want to think about some complex Java logic and then embed some SQL query data inside it. Uh, However, that is not the case in the property graph. In the property graph, any major property graph query languages will have a graph algorithm embedded, so that you don't really need to switch the context. You just directly write a query and that's it. So now let's talk about Neo4J. So Neo4J is a graph database that use property graph data model with a query language called Cypher. Uh, in the graph database domain, there's no standard query language. I won't say yet. Many vendor-dependent flavors. For instance, we have a query language called Sparkle that is used for RDF. We have a Cypher, Gremlin, and many extra like vendor-dependent query languages that for property graph. For example, we want to find the co-stars of the office. In the Sparkle, we may write something like this. However, in Cypher, the exactly same query will become something like this, shown in the green. And in Gremlin, we will have something like blue. As you can probably tell by just directly glance at it, at those three queries, we can see that the Sparkle and the Cypher has this a little bit familiar with some similar like a SQL in terms of like a declarative style. So there has been ongoing standardization effort called that's called graph query language. So that's whatever I talk here or you may find online that maybe become a legacy very soon. But that's what it is right now. So if you want to use different graph models, then you may run into different query languages. So now let's do a quick demo of create the office crew graph that we have been talking about in Neo4j. So I'll walk through the syntax first, and then then you can type along if you have already set up the Neo4j sandbox. So here the syntax actually is pretty simple. So here we want to have a keyword create that's Neo4j's keyword that's indicating we want to create a graph. And then we first, the first thing we need to do is that we define all the nodes first. So in this case, we have 3 nodes. First one, we have N1. And that's actually just a node name, so that or the node variable, if you prefer, that allow us to easily reference a certain node in the Neo4j's query language Cypher. And with N1 has a label called person, and we have 2 pairs. The first one is the name Stephen Carl and the gender male. So that's exactly matching the whatever shown here. Second, we have another node again with a label person, and we model the second actor, BG Novak, and he's a gender male. And the third node, actually we assign different label. We have a label called TV show, and we have just only have one pair, so title and office. So as you can see, after we have done with all these 3 nodes, actually now we can switch to define our edges. So first of all, we define this edge that's going from N1 to N2. So we have a node N1 that we use the parentheses in the Cypher to indicate that is node, and we use square brackets in the Cypher to indicate that is edge. So we have N1 that is a direct edge from N1 to N3 here, and such edge has a label called xin, and similarly we have 2 attributes, row and ref, each with this value, Michael G. Scott and Wikipedia. Similarly here as this edge, But in here, we don't really, this edge shows that we don't really necessarily like want to have any attribute. If we don't really have any, we just put anything, just put a edge label here, and then we are done. So now let me show the, actually let me use this Neo4J to showing you like what exactly this look like. After I showing this one, you will have a hands-on session that will create some other property graph. You can play this on your own. We'll have some time for that. So in this case, I just directly copy the code here. So I'm already inside the sandbox. So if you are already here, so here's the sandbox, and I just create a blank sandbox here. I paste in my data, so you don't really need to have the semicolon like here. So you just actually kept the control. You just run it. So here actually says created successfully. You have added 3 labels, create 3 nodes, sets 9 properties, create 3 relationship. That relationship is the word that used by Neo4J. That's actually the same thing as edge. So we can actually see the table that actually we can query the table here. We use this query. And then we can click on this graph icon, and actually it shows that we have the office, and we have 2 relationship Axine produces, and we have a BJ Novak and Steve Carl, and we have another edge Axine. Okay. So now, so let's practice. So we will have 5 minutes for you to create actually your own. We'll create the org chart of the paper company Dunder Mifflin Scranton branch in the Office TV show. Just for you to know that we don't really in the old edges we don't really have any property attributes. We just all use keywords and managers. And there are some useful commands. For instance, you can see the graph with this query, and you can relate the graph with this query, and in case there are multiple attributes, like for instance the property value actually in the Neo4J can be a list. So in that case, you use the square brackets to define a list. For instance, some person may have a role that is he works as a sales, but he also works as assistant regional manager. So actually, this is the org chart of Dunder Mifflin. You will have 5 minutes, but you don't need to like create all the graph. I will provide the data for you after the 5 minutes, so you can just start play around. For instance, you can start just create one single node. David Wallace, that's serves as a CFO of Dunder Mifflin, that he works in the management department, and that he has a node label person. So let's get started, and let me know if you have any questions in the Zoom chat, or just speak out loud. Oh yeah, sorry, yeah. Uh, you mean here is it? Can you look at? Can you see the sandbox, the web browser? Oh yeah. You mean you want to see the query again? Yes. So basically, it's more like a command line prompt. Yeah, here is actually I'm typing the query. You can just it's what it is like at the very beginning. So you have a prompt here, and then you can type in the Cypher query here, and then click on this triangle button to run that query, and they will run it for you. And then you can scroll down like this and to see all your past query history. Oh yeah. Yeah, sure. Let me get a chat. Yep. Uh huh. Uh-huh. Yeah. You can use a different label. That's basically the variable name. You can define your own variable. Oh, yeah. I think so. Yeah, you have to. They have to be different because in the query they will just use those variables to query them. So they has to be unique. Yeah. So actually, says invalid. Okay. So actually, Uh, let me actually just share the screen. Actually, we already have we have 5 minutes already up. So actually, let me share the actually the query the data I have pre-compute. Actually, I have I don't know how to say it. Just pre-compile it. Actually, let me show the link here. I'll use this link to basically to type all the commands here to share all the commands that we're gonna use in this session here. Uh, 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 yes, using columns. Yes, Mark, you are exactly right. Yes. So can anyone has anyone seen the GIS that I shared here? Yep. So actually, the first thing actually actually you can that's actually show the whole how the whole graph is created, and um, if you need to and actually if you need to also paste in these two commands here that um, basically serve as the first one actually serve as a querying the whole graph, and the second actually is the basically deletes the whole graph. So I paste it as a comment in the same link. So let me know if you have seen any question there. So actually let's move on. So uh, from current slide. So we already seen how we can create this, well, or part of it, the Dunder Mifflin org chart that actually will be served as a running example for the rest of the session. So let's now talk about graph query languages. There are two important usage patterns for graph query languages. The first one is called graph pattern matching, and the second is called graph navigation. We'll talk about these two in greater details later on. So the thing is that we focused on Cypher in this tutorial. However, any significant graph query languages will have these two important patterns in their languages. So whether it's for instance, the Gremlin, you will see the exactly same patterns, but they will have a different syntax. So, so whatever we talk here will apply to other languages. Uh, let's first talk about graph pattern matching. So a match is actually a mapping from variables to constants, such that when the mapping is applied to the given pattern, the result is roughly speaking contained within the original graph. Or you can say that the pattern is a subgraph. For instance, we want to find the co-stars of the office, and we have exactly the same property graph, the office crew graph as we shown earlier. And now we have a graph pattern for Q1. So what's the difference between, what's the new here is that you can see we have exactly the constants here is the N2 TV show that match with this node, N2 TV show with the title The Office and title The Office. And similarly, we have edge X in and X in. Um, but however, the new thing is that we have this label that has a variable name called x1, which indicate that this is some label, that's some variable that we wanted to bind to some constant in the office group graph, such that this whole pattern holds. And similarly, we have a variable called x2 here for the other node label. So if we use this graph pattern to query against the office crew graph, and what we get actually is shown here, which is x1 can be bind to Steve Carl, and x2 can be bind to BJ Novak. And however, actually, The pattern same matter if also applied if we actually switch between x1 and x2, meaning that we bind x1 to BG Novak and x2 to Steve Carl. And actually the result set, if we talk about in the graph database world, we call it matching. We call it matching for Q1. Does anyone have any questions with this slide? Okay, so that seems everyone seems okay with this content. So let's talk about graph pattern matching in Cypher. Actually, Cypher has no repeated edges and bag semantics. Actually, bags is exactly the same bag that we have been talking about in the SQL. No repeated edges, which basically means that we cannot have two different variables mapped into the same edge. You can look up online. I don't dive into more in the details on this topic, but let's first talk about the syntax. Syntax, we have exact same query that find co-stars of the office, and first we have this keyword called matching, which basically we specify that we want to do a pattern match. Then we'll have this x1 person. That x1 actually is a new variable that shows up in this the runtime of Cypher that indicates that it's some variable that we want to find out the answer. And similarly, we have x1 has to connect to TV show nodes through an incoming edge with an edge label called xin. So there are lots of patterns out there that this is a link to the Cypher menu. So actually, let me type this one in the sandbox to see what we get here. So first of all, let me actually delete the graph that I previously created. Sorry, not the. I don't need to delete that one. I think we still need to use that. Oh yeah, I think I forgot to share this one. Yep. Yep. Uh, I think you don't type. I think you just don't need to type this arrow key. I think that should work. Otherwise, you need to create a reverse edge. Yeah. So actually, let's type in actually in the sandbox to see how the query looks like. So we have this match as keyword, and then we have actually first one. Actually, you can see the sandbox actually doing this interactive prompt for you. Uh, um, for some reason, okay, I think I think this one should work. And we have x1 as a person, and then we want to have another node that's called. Actually, let me type. Okay, yeah, I use a name called TV show. Actually, let me start from clean. And then I can just recreate the whole graph again, just in case. Okay, so we have this one, then we do type matching. We have x1 as a person. We have an edge called xin, and we have this edge has to go through the TV show. For some reason, it doesn't shows up, and we'll see. So we have another xin, and then we have x2 as a person, and then we simply just oh shoot, yeah, shift return x1 and x2. Yeah, for some reason, yeah, my code doesn't seem to work here, but I believe I do have some query here. Let me actually see if that's actually I made some typo. Just give me a second. Interesting. Yeah. Anyway, I think there's probably some error set up in my here. The query should run return some result. But let's actually start some time to spend some time to see actually get practice. Actually, let's first see some examples first. So first of all, we use like want to see who's inside party planning committee. So here actually this is actually what a Cypher query look like. We first match any nodes with a label called person, and then we have a where clause to specify. Okay, we want to find this party planning committee string inside its one of the attribute department. So with p dot department to reference, it's p any like the nodes that has a property key department, and then we want to return p dot name, which will return the corresponding name property value. And the second query we want to look at is how many people does Michael directly manage. This is query. So we match p person. So basically here we specify a pattern here that we have a p as with a node label person, and we have an edge managers, and we have another node with n as a label, and we have n as variable name, and then person as a node label. And we have to specify where is n.name equal to Michael Scott, and then we return a count p, which in this case count is a built-in function that counts number of nodes that will be matched here. Okay, so let's practice. So let's find we have another like 5 minutes here to basically can think about how we can find all the employees that are directly managed by someone that reports to Michael. And the second query is that does Michael directly manage more employees than Jim Halbert? Let me know if you have any questions. Yep. Yep. If there's no managed by edge label there, yeah, I think probably there is something that's in the Neo4J, but in that case, I just switch. So in this case, since we don't really have a managed by relation, so basically, if we have an unmanaged P, that means P is managed by N. Does that make sense? Oh yeah. Yes, some query language will create a reverse edge automatically for you, but I'm not sure. Neo4j does that. Maybe we can you can look up in the manual later to see if they actually do that. If there's a special mode that can turn out that will turn out that behavior. Yep. Mm-hmm. Uh, yeah, there's I think that is I think there definitely does. I think that's probably has something with N1 here. That each one is actually bound to a different variable. So if actually let me actually try this one. If we can have a N1 here, and then we just actually. I think N1 actually is a unique one to reference any given unique node. So if you have a multiple ones, then we can just reference that with their variable name with like say n1 is Michael, n2 is Michael. We want n1 Michael, so we just match n1. Yeah, yeah, I think so. I think there's a way. Again, I think that's it's a little bit complicated, a little bit advanced usage. So basically, we can first basic query whatever the value out, and then we assign it to a variable to be used later. Yeah, again, I don't really have a definite answer here, but like there's some they will talk about something on the Neo4J website menu. So. Yeah, I think that is definitely one of the common usage that it should have the support for that. Okay, cool. Mm. Okay, so actually let's take a look at them together. So actually the first query actually looks something like this. So um, here actually we have a match. P has a name Michael Scott and the manages here in the query by someone. Actually, you don't really need to type in anything if we really don't care whether we only care that it's a node. In this case, we know that in the public graph, they only have a node with a label person. But if we in a like say some social network, we want to match by someone, that someone you can specify is a label called person. We just omit the label here, and then it says manages someone a queue, and the queue is just another node. So and then we just return queue.name. Let me actually try run the same query here. Um, uh, see, let me see actually. Yeah, here. Yeah, here actually you can see that we find all the person that's actually indirectly matched by Michael. That we got a list of names. And similarly, we have second query is does Michael directly manage more employees than Jim Halbert? So here we have we have to use two matches here. The idea is that we want to first match all the person matched by Michael Scott and count them. And then we use another match that basically count the number of people matched by Jim Halbert, and then we see which count is larger. Here is that the first match, each match where can be thought as a select from where statements in the query, and we use a with a clause as a special syntax to break between two matches, because otherwise, for instance, as this query will show that if we just directly use the two match here without any with, it will work exactly like a join clause. So we have a Michael Scott person of Michael Scott and the person matched by Del Philippine, and then if we just use the two matches here, then we'll have a cross product between this P and Q. Okay, so now let's talk about graph navigation. Graph navigation is a mechanism provided by graph query languages to navigate the topology of the data. There are two important query classes here. First one is a path query, and the second is a path query in combination with a graph pattern matching. and we call it a navigational graph pattern. So previously we match a graph pattern, and now we want to match a path pattern. So a path query, a little bit formally to define it, is has a general form of p equal to. Oh, I see. Actually, I see some question in the Zoom chat. Oh yeah. Oh, oh, oh yeah. Thank you for that. Yeah, thank you. So we have a form p equal to x alpha goes to y, where alpha specifies some conditions on the path that we wish to retrieve, and x and y are the endpoints of the path. Sometimes, most of the time, alpha actually are represented using regular expressions, although the syntax may be different than the regular expression that you're probably familiar with from the programming. For instance, we have the exactly same of the office crew graph, and we have a Q1 that we want to find the co-stars of the office. Then, if we want to have a represent in the path query, this one is actually a more theoretical representation of that path query. So we want to define a path that goes from a node X and to the node Y. And we have a constraint called xin and xin minus. Xin means that it's an edge that goes from X to Y. And xin minus indicates that it's a reverse direction. So it's an edge goes from Y to X. And we use a dot to concatenate them together. That means that there has to be a path that first has an edge that goes from X to Y, and then we follow on the reverse direction of another edge that goes from that's called xin minus. So let's actually see an example here. So again, Cypher has a non-repeated edge back semantics that I won't talk about more in details, but you can look up online. So we have exactly the same query. Actually, you can see that this query doesn't really like something new, because the only thing new here, we only just assign this pattern to a variable called path. But the difference here is that rather than we do a graph pattern matching, we actually return a path. Actually, in Cypher, this path query and graph pattern matching may not look very significant different, but in some other languages they do. So just that Cypher thing that makes this they blur this kind of like two pattern usage. So if we run this query inside our property graph, we actually will get two passes. Actually, the first pass, the reason why we got two passes is because actually both P and Q can actually map to Steve Carell or BJ Novak. So if we map P to Steve Carell, we have a path that goes from N1 to N3. And however, if we, on the other hand, if we have a P mapped to BJ Novak, then we have another path that goes from N3 to N1. So let's talk about another navigation pattern usage that's called navigational graph pattern. So we can actually combine the path query with graph pattern matching by allowing edge labels in the graph pattern to be paths. So for instance, we have a Q2 called, we want to find all the people that Michael Scott manages. So it looks something like this, the corresponding pattern. The important thing here is that you can see this manager's edge label have this star 1 dot dot. That is a Cypher way to write a regular expression, basically symbol plus, meaning that we can have we want to match the edge label managers one or more times. So that means that we have a person P that goes to person Q through one or more managers edges, and such P person has to be a Michael Scott. So let's see an example. We want to find all the Dunder Mifflin employees that are on the same level as Michael Scott. So this is what exactly the query look like. So here we use two matches again. So we have a first match P1, which is a path 1. that matches person n, and then we have as you can see, we have this edge label manages star. Star here is that means we can have a 0 or more, exactly like star in the regular expression. And similarly, we have another match called P2. And the constraint we have is that we want to have a length of P1 has to equal to length of P2. And we don't really want to have M and N equal to together because N is a name Michael Scott, so we want to find other persons, and we return N. Actually, let's query the same data actually in the relational model. Um, so we exactly have the same query. As you can see, that probably we have already used it from the homework 7, that we have to use some CTE in the SQL that Dan will actually talk about in greater detail later today. We just skim through it. Actually, we use a recursion in the SQL that we have a base case, and we have a union with another recursion. And the point I try to make here is that you can see how simplified the query can become if you're actually using the graph query compared to we use SQL. So let's practice. So we have two queries. The first one is that we want to find out does Jim Halbert manage Phyllis Lapin? And the second query we want to find is that find all the people that are indirectly managed by Michael Scott. So again, we'll have 5 minutes to play around with this. And let me know if you have any questions. Yep, yep. Uh, uh-huh. Mm-hmm. Uh, which part of the query is it this one? Okay, cool. Okay, so now let's take a look at these two queries together. So we have this first query. We have a manages that we have a pass p person that manages one or more hops to the q person, and we have the p has to be a Jim Halbert and q has to be a Phyllis Lapin, and then we basically count if there's any pass that's out there. Basically, we count pass if it's greater than 0. That means Jim Halbert indeed manages Phyllis Lapin. The second query is that we want to match a pass that goes from Michael Scott, actually multiple hops that goes to some person P2. That basically the first one is has to be goes to one or two hops, basically by hop I mean edges, to some person we don't really care. But that person has to have another edges that manages that's one or more to the P2 person, and then we return the distinct P2. The reason is that here's a question actually, why do we use distinct P2 rather than distinct pass? The reason is that actually in the property graph, since it's a pass, actually there can be multiple passes that goes to the same person. So we actually, if you actually count using like if you actually using pass here, or like not may not be true this query, but for some other queries that if you have a passes that the pass number may not be equal to the people number. The third one actually is the last one is actually the graph algorithms in Cypher. So Cypher and many query languages allow user to directly embed graph algorithm inside the query. So for instance, we want to find the shortest path between David Wallace and Andy Bernard. This is actually what the Cypher look like. As you can see here, we have a keyword that shortest path. Actually, that is a built-in functions offered by Cypher that allows you to find the shortest path for a given path that you have defined in the parentheses. In this case, we define a path that goes from David Wallace to Andy Bernard, and we want to return such path. However, there are many more graph algorithms that are offered by Cypher. For instance, PageRank centrality, connected components algorithms, and many others. So there's have a full online menu that you can look up to play around. So in conclusion, in this session, we actually introduced the edge label graph and the property graph, and we discussed the difference between these two, and of course we discussed more generically how the graph model different from the relational model. We briefly introduced three query languages: Sparkle for RDF, Gremlin, and Cypher for property graph. But we will focus most of our effort on the property graph and Cypher. We introduced three important usage patterns in graph query languages. First is graph pattern matching. Second is path query, and the third is navigational graph pattern matching. And we demonstrate and practice those usage patterns in Cypher with Neo4J. And you can use these slides as a starting point to know more about Cypher. So even though in this class we talk more like about on the Cypher, actually we cannot ignore Gremlin. Gremlin is actually a very important query language that have a totally different flavors, more imperative flavor compared to Cypher, and it's still very popular. I believe Amazon Neptune they offer Gremlin, and as I believe soon they will offer Cypher as well. So you also, if you're working the Gremlin domain, then you need to learn a little bit more about Gremlin, how Gremlin used as a query language to query property graph. And also I have some code that's online that's basically use a different set of data, but I use exactly same query writing Cypher, SQL, and data lock that Dan will talk about later. And also all the code for this tutorial I actually post online, and slides are available from online, so feel free to check out later after the class. So that's it. So if there's any questions, so feel free to ask. If there's no more, I'll just give control back to Dan.